feel free to stop. So today I'll be talking about collaborative bandits with latent clusters. And in this talk, I'm going to discuss how to design algorithms that effectively make use of collaboration across users to learn optimal policies quickly and jointly for several users together in a large-scale sequential decision-making task. So this talk will be based on several papers that have been published at ICLR, AI Stats, and a couple of recent submissions. And finally, this work has been done jointly with my colleagues at Google, Arun Sai Sugala, Karthikeyan Shanmugam, and Pratik Jain. Okay. So there will be 4 parts in this talk. In the first part, I will introduce multi-user, multi-armed bandit optimization problems and will highlight the importance of collaboration across users. In particular, I will discuss that if we try to solve a bandit optimization problem separately for each user, then it will lead to a very high cost. On the other hand, if we try to collaborate across users, pool their data together, and solve the optimization problems jointly for several users together, then it leads to a significant reduction in cost. Okay. In the second part, I will dive deeper into our proposed algorithms for collaborative multi-armed bandit optimization problems. In particular, I will start off with a warm-up, a simple greedy algorithm that collaborates across users, but its cost is suboptimal. Okay. And next, we will move on to our main proposed algorithm that we call Lattice, or latent bandits via matrix completion, which obtains optimal regret guarantees under certain assumptions. Okay. Third, if time permits, I will also discuss a very simplified and practical version of our algorithm that shows great empirical promise in a large-scale real-world application concerning maternal healthcare that we are currently pursuing with the AI for Social Good team at Google and an NGO called Arman. And finally, I will conclude with some major takeaways from this talk. Again, please interrupt me if you have any kind of questions whatsoever. Okay. So let me begin with an introductory slide on bandit optimization. Bandit optimization is a very general framework for designing sequential decision-making algorithms, especially when the underlying dynamics of the environment are unknown. Okay. So bandit optimization problems and algorithms have been studied significantly in the theoretical literature. And moreover, it has also seen great empirical success in applications where there is a need and scope for sequential decision-making algorithms. So let me provide some examples of such instances. Consider a recommendation system such as Netflix, Amazon Prime Video, YouTube, Spotify, etc., and consider a user who is subscribed onto one of these platforms. The goal of the recommendation system is to recommend likable videos or movies or items in general to the subscribed user. But the question is which particular video or which particular movie to recommend. Remember, at the very beginning, the recommendation system does not have any idea about the preferences of the user. So what can it do? Okay, one possible solution might be to recommend a small set of exploratory videos or movies and obtain the feedback of the user. Okay? And from this obtained feedback, it can learn something about the user taste and subsequently recommend a more likable set of videos. Gradually, with more and more feedback data, the recommendation system should be able to recommend more likable videos. Right? This is an interactive process and necessitates a sequential decision-making algorithm. Similar sequential decision-making tasks also arises in several applications in AI for social good, such as healthcare, wildlife poaching, etc. However, modern applications cater to millions of users and items jointly. Just to give a taste of the scale of the modern applications, let me state some statistics about YouTube, a very popular video sharing platform that I guess everyone in the room knows about, right? So 31% of people on Earth use YouTube today. There are more than 51 million active channels on YouTube. And finally, 70% of videos that are watched by users are via recommendations. This highlights the importance of a good personalized recommendation system. Users don't go into the search box and type the name of some video they want to retrieve and watch. They watch videos that are recommended to them by the system. So at this point, let me give a very brief overview of multi-armed bandit optimization setting for a single user or a single agent. In this setting, as I mentioned, there is a one user or agent. There is a time horizon of T rounds. There are a set of items or arms, as they're called in the bandit literature. Now, the goal is to design a sequential decision-making algorithm that at each round will recommend an item to the user. The user will consume that item and give some feedback, say a like or a dislike, based on the preferences of the user. Okay? So this feedback can be thought of as some sort of reward to the recommendation system. Based on this feedback, the goal of the sequential decision-making algorithm is to recommend a new item in the next round. Okay? The new item is recommended based on the feedback of the user until that round. Now, the overall high-level objective is to maximize the reward. That is, maximize as many and as much likable videos that can be recommended to the user. Now, in typical bandit optimization problems, there is an exploitation dilemma. The question is, how much should a sequential decision-making algorithm explore in order to learn the user preferences well? It turns out that the optimal algorithms in this setting have an exploration cost that scales as a monotonically increasing function of the number of items and the number of rounds. This is intuitive because if the number of items in the setting is large, the algorithm needs to explore more in order to understand the preferences of the user towards all the different items. Similarly, if the number of rounds is large, the algorithm needs to explore more so that it can be more confident about the learned user preferences. Okay. Now, although single user multi-armed bandit optimization problems have been studied significantly well, not much is known about its generalization to the multi-user setting. Now, consider a setting where there are several users who are playing the multi-armed bandit optimization game with the same set of items or arms. And this setting captures recommendation systems such as Netflix or YouTube again, where there are millions of users who are subscribed onto the platform. There are millions of available videos or movies where each of these available video and movie correspond to each of the arms. Okay. So, of course, none of the preferences of the users towards any of the items is known at the beginning. Okay. Now, the key thing to remember here is the amount of data per user is very limited. For instance, I would watch only a small number of movies among the total number of movies that are available on Netflix, right? However, the goal of the recommendation system is still to provide personalized recommendations to each of the subscribed users. Now, this necessitates a collaboration across the users. Somehow, we need to pull all their data and solve the optimization problem jointly. This is because if we insist on trying to solving the optimization problem separately for each user, it will lead to an incredibly high cost that scales as a monotonically increasing function of the product of items and users. Again, this is quite intuitive because note that in this setting, the total number of unknown parameters or learnable parameters is actually the product of the items and the users, corresponding to the preference of each user towards each item. And that's why the exploitation cost scales with the product of users and items. Yes, please.
So let's say I find that when I look at psychology, what from so the corresponding
right? That's a great question. So what you're proposing is some kind of diversity constraint. that we need to show a variety of items to the users in a real world practical recommendation system. So as a matter of fact, this is a great follow-up to our problem. And we call this exact constraint as a blocking constraint, where we impose the constraint that at each round, that as any particular item cannot be recommended to a user more than once. Okay, so if I have that constraint, then it implies that we can only recommend any item just once to each user. And it turns out that our regret guarantees or our all the theoretical and algorithmic results hold also under the blocking constraint. And this is actually one of our submissions at NeurIPS. Yes, please. Right. So we can account for any kind of sub-Gaussian random variable. So a like or dislike is a binary random variable, 0-1 binary random variable, which is a special case of sub-Gaussian. So the user can also rate, as long as the rating is bounded, which is usually is, for example, 0 to 5 maybe. It's a sub-Gaussian random variable, and our system can handle that. Does that answer the question? Oh, so you. Great question, actually. So maybe not an explicit feedback, but the feedback is implicit from some kind of review or the video length that you have watched. Yeah, actually, I don't have a concrete answer to that, but we can, of course, design several metrics or several heuristics to obtain some kind of implicit feedback from that. Of course. And as I stressed that our setting can handle non-binary reviews or ratings. It should be sub-Gaussian. That's it. Yes, please.
I say you recommended me a video, but I just don't give you a feedback. So you get the information that, okay, we did recommend this video. So, but you didn't get a feedback from it. Can you take advantage of that information?
But without any kind of signal whatsoever, it's not possible to learn anything, right? So there has to be some kind of signal, maybe implicit, as he was mentioning, like, for example, some text or watching the video until some extent, maybe implicit, but there has to be some kind of signal regarding whether the user has liked it or not. Does that answer the question? Okay. Any other questions? Okay, great. So as I mentioned, the exploitation cost scales with the product of the items and users, because those are the total number of learnable parameters and unknown parameters in this setting. And such a huge exploitation cost is infeasible in modern applications with millions of users and items. Okay. So the question is, how can we make the problem feasible? How can we somehow reduce the number of learnable parameters? Okay. So we introduce our model with a cluster structure constraint on the true reward matrix. So recall that at the very beginning of the algorithm, the preferences of the users towards the different items are unknown, right? So we have an associated true reward matrix corresponding to all the users and the items that are unknown at the beginning. These correspond to the learnable parameters, actually. Now we impose the following constraint on the true reward matrix. We assume that the true reward matrix satisfies the following cluster structure, where the set of users can be partitioned into a small number of unknown clusters, okay, such that users in the same cluster have identical rewards across the items. It's not okay. So if you look at the first two users over here, they belong to the same cluster because they have identical rewards across all the items. And again, the third and the fourth user belong to the same cluster because they have identical true rewards across all the items. Now, again, this is just an assumption that we make on this true reward matrix. I emphasize that we do not know the cluster memberships, that we do not know a priori which user belongs to which cluster, nor do we know the entries of this reward matrix. All these things are unknown at the beginning. Yes, we do know the number of clusters. Actually, as a matter of fact, an upper bound on this is sufficient for us. So this kind of cluster structure assumption has been used popularly in the literature. Okay, this is because it's satisfied approximately in several real-world datasets. For example, even if there is a large number of users in the system, you can expect that a significant subgroup will like, say, sports movies, a significant subgroup will like, say, drama movies, and so on. And as a matter of fact, here I have shown a plot of the rewards of several users towards the many different items in the movie lens 10M dataset. And as you can see, the cluster structure across the users is pretty evident. Okay, so what does the cluster structure assumption mean? It means that you can represent the true reward matrix as a product of two tall matrices. Can you see that? If you notice carefully, the first tall matrix can be thought of as a user embedding matrix. Each row belongs to the standard basis state of standard basis vectors and captures the true tastes of the users. The second tall matrix, or the transpose of the matrix actually, corresponds to the true characteristics of the items. So if you think about it, the total number of learnable parameters is now just the number of users, because you need one entry for each user embedding vector, and the number of items times the embedding dimension. If the embedding dimension is small, this quantity, the set of learnable parameters, is much smaller than the total number of unknown parameters in the true reward matrix, which is the product of users and items. Yes, please. Yes, that's a great question. For now, we do assume them to be disjoint. But yes, we can also go to much more general stuff. Yes, yes, of course. This true reward matrix is unknown, but what we observe is a noisy version of these entries. Definitely, I'll show that when I define the setting rigorously. But this is the true noiseless version of the rewards. Yes, exactly. If the algorithm knew this, it would have been done. Yes. One more insight. If you have the cluster structure on the true reward matrix, it also turns out that the rank of this true reward matrix is small. And as a matter of fact, the rank is bounded from above by the number of clusters. This is also evident from the right-hand side representation, right? Okay. And this is a fact that we are going to exploit crucially in our algorithms, by the way, that the true reward matrix is of low rank. Okay, so as I mentioned, that the cluster structure assumption is pretty common in the literature, and our work on multi-user, multi-armed bandits with the cluster structure has been studied in the past as well. So this work, our setting was first motivated and studied by Millard and Menon in 2014. But they made one of two assumptions. They assumed that, number one, they knew the cluster memberships, which users belong to which cluster. Or alternatively, they assumed that they knew the true rewards of each cluster. Okay. If you make either of these two assumptions, then it turns out that it's quite simple to design algorithms that obtained optimal regret guarantees. Regret is a cost function, by the way, which I will define later. Now, our problem setting was then taken up by Gentil et al. In 2014 and 2017, who studied the problem from a linear bandits perspective, which is more general. They did not assume anything about the cluster memberships or the rewards, but when their guarantees were translated to our setting, they were far from optimal. And in this work, we demonstrate a new algorithm called lattice, or latent bandits by matrix completion. Again, we do not assume anything about the knowledge of cluster memberships or the true rewards. And we show that nevertheless, lattice obtains the optimal regret guarantees. Yes, please. We do not assume that, and that is a strength of our work, actually. Right. So actually, yeah, I mean, you can have two clusters which are very much the same, very much close, let's say. Or yeah, artificially, you can also think of them as being two clusters. So as I mentioned, if you have an upper bound on the number of clusters, it is sufficient. And if they are very close, let's say, then you can treat them as a single cluster for a long period of time without any harm, right? So that is the intuition that we have. But we consider this as a strength of our work, that we do not need to know any gaps between in the true rewards between the clusters a priori. Okay, great. So in the current recommendation systems, the popular approach is to use a two-tower model, where for every user and for every item, we have a set of observable user features or item features that are passed through some deep neural networks and used to construct user and item embeddings. And then the preference of the user towards the item is modeled as a similarity function between the user embedding and the item embedding. So this approach is useful only when you have a good set of user features and a good set of item features. But recall that in our setting, the user embedding vectors and the item embedding vectors, the tall matrices, remember, they were latent or unobserved. Okay. So our approach can be used to enhance the popular two-tower model when the user or item features are hard to construct. For example, in healthcare applications, where the users will not be readily giving up the feature vectors due to privacy concerns, right? Even in settings where the user features or item features are corrupted, misleading, or non-informative, our approach or setting can be used to enhance the popular two-tower model. Okay, so to summarize, modern systems have millions of users and items. And if we treat each user separately, it is very inefficient, requires a huge exploration cost. On the flip side, if you treat all the users as same, it's an equally bad solution. Doesn't lead to any sort of personalization. So the key assumption that we make is that the user or item features that are unknown, again, belongs to a low dimensional space, and the user features belong to a set of standard basis vectors. What this implies is that the true reward matrix has a cluster structure and also a low rank. Okay? So what I will show in the next section is that our problem basically boils down to an online version of low rank matrix completion, which comes with its own associated set of challenges that I'm going to discuss. Okay, great. So let me start this section by rigorously defining our problem setting. Suppose we have M users, N items, and T rounds. Okay. And we also have a sequential decision-making algorithm, which at each round recommends one item to each user. Okay. The recommended item can be different for the users at a particular round. Okay. Now, at each round, every user comes up, consumes their corresponding recommended item, and gives a feedback. Again, say a like or a dislike based on their preferences. Yeah, please. From a matching problem. So you are going to draw edges between users and items based on their similarity preferences, right? So right. So first of all, we do not know about the preferences, right, at the very beginning of the algorithm. So without that information, you cannot have another algorithm. That's the goal, actually, to learn the preferences of the user and also to recommend new items. So so when you are thinking of matching, I think that's the main bottleneck, because you don't know the preferences, first of all. And even if you knew all the preferences, then you would have been done. Done. Something else. Right. That's also one other constraint for matching. Right. Yeah, I'm not probably able to see what the algorithm for matching will be like in this online setting, but maybe we can discuss it offline. Okay, great. So yeah, at each round, the user comes up, consumes a recommended item, and gives a feedback. Again, say a like or dislike based on their preferences towards the item, corresponding item. Now, based on the feedback of all the users jointly until that round, the recommendation algorithm or the sequential decision-making algorithm will recommend or output a new set of items at the next round. Okay, so this is an interactive process that will go on for the entire duration of the T rounds. The goal of the decision-making algorithm is again to recommend as many and as much likable videos or items as possible to all the users. So with this setting in mind, let me rigorously define the notion of reward. So for a particular user at round T, suppose the recommended item is denoted by row UT. Okay. So in that case, the reward at round T for user U is P U row UT. This corresponds to the entry of the true reward matrix for the user U and the item row UT that was recommended by the decision-making algorithm. This is the true reward. Okay. Plus we have some sub-Gaussian noise. And so this noisy reward generalizes the binary setting because a binary like or dislike is a sub-Gaussian random variable as well. Okay, great. So with this notion of reward, let me also define the regret or a cost that is studied in these online settings. Now, I should mention this point. Please, there's no need to remember all these notations. I have just put it here for the sake of completeness and to have the definitions out there. Okay. Okay. So if you fix a particular user U, then what is the best thing that the recommendations or decision-making algorithm could have done in hindsight? Or if it had known all the true rewards? The best thing that the decision-making algorithm could have done is to simply recommend the item with the highest reward throughout the entire set of T rounds to the user U. This is the best thing it could have done. But instead, it has recommended a sequence of items. So we compare the two things. We compute the difference in the best item that it could have recommended in hindsight for the entire T rounds versus the sum of rewards of the sequence of items that it has actually recommended to the user U. We also have an expectation to take care of the randomness in the algorithm and in the noise. The overall regret is defined as the average of this difference across all the users. So we have an M inverse at the beginning. Okay. So this is the quantity that we seek to minimize. One second, sorry. Sorry, one second. Yes, please. Sorry. I see. So yeah. Actually, we do have M copies of the same item. We can. Right. And even like as I answered your question, I guess. So we can put a constraint that you can recommend an item to a user only once, which we call the blocking constraint. And it turns out that all our results also extend to the blocking constraint. This is a newer result that I have not talked about here in this presentation, but it's there in a submitted paper actually. Of course, what is the best thing then the decision-making algorithm could have done in hindsight? The top T items, right? The The regret definition itself changes, but the results remain same. Okay. Any questions at this point? Because I want the problem setting to be clear to everyone. Yes, please. Absolutely, great question. Yes, the rewards or preferences can change over time. This is a dynamic version, and it's a great follow-up. I don't know the answer to this question, at least the theoretical question. Yes, it hasn't been fixed. Yes. Yes, please. Right. So, okay. So sub-Gaussian random variable is a special class of random variables whose moment generating function is bounded. Basically, it has a at a high level, we can say that it has a tail which decays exponentially fast. This means that the probability of the random variable being larger or smaller than a particular value is very small. Okay. With high probability, the values are, let's say, around its mean. Great question again. Multimodal might not be sub-Gaussian. So no. But sub-exponential, heavy-tailed, there are many classes of random variables that it rules out, actually. Okay, great. So let me move on. At this point, let me show our first algorithm, a simple greedy algorithm. Okay? What the greedy algorithm does is to split the entire time horizon into two parts, the exploration component and the exploitation component. In the exploration component, the greedy algorithm does something very simple, nothing fancy at all. For each user, at each round, it uniformly samples an item and recommends it to the user, gets its feedback. Okay? So at the end of the exploration component, we will have some sets of likes and dislikes corresponding to the recommended items and their corresponding feedback. This sets of likes and dislikes in general correspond to a set of partial noisy observations of the true reward matrix, right? So the question is, can we estimate, can you see the slide? It's, wow, this. Yeah, okay. So the question is, can we estimate the entire true reward matrix from this a small set of partial noisy observations? Okay. Now, this generally would have been an impossible task. How can you estimate an entry even without observing it, right? But remember, we assume that our true reward matrix has a cluster structure, and therefore its rank is small. And it turns out that for matrices whose rank is small, you can complete the matrix, that is, estimate the entire matrix from a small set of partial noisy observations under certain assumptions. Okay. So what we can do at the end of the exploration period is to solve an optimization problem. We can minimize the squared error on the observed entries plus have a trace norm regularizer to account for the low rankness of the true reward matrix. We can solve this optimization problem to get an estimate of the entire true reward matrix. Okay. So once the greedy algorithm has this estimate, it will simply go on recommending the item with the highest estimated reward for each user. So in the entire exploitation component, the second period, the greedy algorithm will recommend the second item for the first user. The greedy algorithm will recommend the third item for the second user and a third item for the third user too. Okay. So again, to summarize, the greedy algorithm is very simple. It splits the entire time horizon. Oh man. Okay. Needs two clicks. The greedy algorithm does something very simple. It splits the entire time horizon into two parts, the exploration component and the exploitation component. The exploration component, the greedy algorithm, for each user at each round, samples an item uniformly at random and recommends it, gets the corresponding feedback. So at the end of the exploration period, we have a set of partial noisy observations corresponding to the true reward matrix. Then the greedy algorithm solves an optimization problem to get an estimate of the entire true reward matrix. And based on this estimate, the greedy algorithm will recommend the item with the highest estimated reward for each user. Okay, yes, please.
assuming more than just low rank. You're assuming that the rows are exactly equal.
Yes, that's a great point. Yes, I am assuming more than low rank, but what I need to use is just the low rank. This is, you might be asking then, why can we not assume the low rank itself, right, on the true reward matrix? So it turns out that for the optimal algorithms, the cluster structure is also necessary for us. This algorithm actually works even when the true reward matrix is low rank. No need for the cluster structure. You're right. Thanks for the great question. Okay. So for the greedy algorithm, the question is, how much exploration data should we use? If we have a longer exploration period, it will lead to a better estimate of the entire matrix. It will make the exploitation period better. But on the other hand, it will also lead to a longer cold start period, which means that the users have been recommended arbitrary items for far too long. Right? In any practical recommendation system, users will be thrown off by such a long period of arbitrary recommendations. So we can optimize for the I don't know how to hide this. Yes, please, of course. Yes.
What is the reason that the need for that item
Right. Well, the short answer is that I made up those values. The longer answer is that the user might have liked the item even though its probability or the true reward is 0.1. Because it has a low rank regularizer, the matrix is supposed to be more towards a low rank matrix. So even if it, let's say, even if it does not satisfy some of the observed data, it will give me an output of the entire matrix, which is closer towards low rank. So that's why it might happen that even though the user has shown a light, because of the low rank structure, it has given the estimated value is 0.1. Right, right. Again, because to conform to the low rank regularizer. And more importantly, I made up this. Okay, so okay. Yeah, so the regret of the greedy algorithm scales with 1 plus items by you. Yeah, sorry. Please. Great question. Here we do not have, we have not made any assumption about similarity across items. To be honest, the only thing that we need to assume is that the underlying true reward matrix is low rank, which also captures similarities in both the user space as well as the item space. So to answer shortly, yes, similarities across items are also captured by offline low rank matrix completion algorithms. Okay. I thought I saw another hand. Okay, great. So the regret of our greedy algorithm scales as 1 plus items by users to the power 1/3 times rounds to the power 2/3. This is actually similar to the cost or regret guarantees obtained for a single user multi-round bandit optimization problem by the greedy algorithm. Okay? But if you notice carefully, the effective number of items that we have is a ratio of the items and users, right? Now, this is important because even if the number of users and a number of items are very large, as long as the ratio is small, we are in business. Okay. This is also intuitive because even if the data per user is very limited, if the number of users is very large itself in the system, then we can get a lot of data in a small period of time. However, the main disadvantage of the greedy algorithm is its suboptimal dependence on the number of rounds. It scales as rounds to the power 2/3. Another big disadvantage of the greedy algorithm is that it recommends arbitrary items to users for a prolonged period of time. We don't want that in a practical recommendation system. So in the next algorithm, we will address both of these issues. Okay. So before going there, let me just quickly go over some theoretical challenges we faced in the analysis. Although the greedy algorithm is quite simple conceptually. Yes, please. Yes, exactly. Because we're getting noisy estimates, we have to like fix some data from which we can get an estimate of the entire reward matrix. More data leads to a better estimate for any noisy, for any estimator in the presence of noise, right? Sorry, I could not follow. Right. Oh, then it would have been very much simpler. Yes, exactly. Great question. If the noise was absent, then we can exactly tell you the number of rounds after which we would have been able to estimate the matrix exactly. This number of rounds does not depend on the length of the total number of rounds or on the value of t. Okay, which means that only after, let's say, a constant number of rounds and its of corresponding data, we could have estimated the true reward matrix exactly. And if we knew the exact true reward matrix, the greedy algorithm is done, right? The regret would have been 0 actually, asymptotically, normalized by the number of rounds. Great question, thank you. Okay, so let me go over the challenges in the theoretical analysis. So although the greedy algorithm is quite, let me just go back. Although the greedy algorithm is quite simple, recall that at the end of the exploration period, we used the offline low rank matrix completion algorithm to estimate the true reward matrix from the set of partial noisy observations, right? And as I mentioned before, this offline low rank matrix completion algorithms comes with several assumptions. Okay. So let me go over these assumptions or the limitations of the existing offline low rank matrix completion algorithms, which we needed to tackle to convert the guarantees into regret guarantees in our online setting. Okay, so first of all, the guarantees of the offline low rank matrix completion algorithm holds only for square matrices. However, in our setting, if we have a rectangular reward matrix corresponding to a very different number of users and items, it's difficult to extend. Why? Okay, a very simple solution could have been to pad a large chunk of zeros to the true reward matrix to make it a square matrix. But it turns out that the simple solution does not work. Again, I must emphasize, or let me reiterate, that the low rank matrix completion algorithms works under a certain set of assumptions, and one of them is called incoherence. What does incoherence mean? Incoherence means that most of the entries of the low rank matrix should not be 0. Okay, because otherwise the partial set of noisy observations might not give you any information about the unobserved entries. However, if we pad a large chunk of zeros to the rectangular matrix to make it square, then the incoherence parameter of this resulting square matrix blows up significantly. And therefore, the guarantees of low rank matrix completion oracles also degrades significantly. So our solution is the following. We take the longer dimension and partition the entries along the longer dimension to create approximately square matrices. Okay? The key challenge is to show that the incoherence parameter and the condition number parameter of these approximately square matrices is not too far away from the corresponding parameters of the original true rectangular matrix. And this allows us to apply the low rank matrix completion oracle to each of the approximately square matrices separately and then stitch up those estimates to get an estimate of the entire reward matrix. The second limitation is that the probability of error usually scales with dimension in the existing guarantees for offline low rank matrix completion. However, in these kind of bandit optimization problems, we need a probability of error that scales with the number of rounds. To have a much smaller probability of failure, we can do a very simple trick. We can repeat the exploration component a couple of times to get several estimates of the true reward matrix. Once we have the several estimates, we can go to each entry and take the median across all the different estimates for the same entry. And such an operation improves the quality of the estimate significantly. The probability of failure is much smaller. Okay. Okay. So let us move on to our next main algorithm, lattice or latent bandits via matrix completion. Okay. Before going on to the theoretical details, let me demonstrate our main results. So as I mentioned before, lattice obtains the optimal regret guarantees. Its cost scales as square root the number of rounds times 1 plus the ratio of items and users. Again, the effective number of items is the ratio of items and users, right? And this regret guarantee is actually optimal in items, users, and the rounds as well. In contrast, if we use a non-collaborative algorithm, such as UCB or Thompson sampling applied separately for each user, that is, if we try to solve the bandit optimization problem separately for each user, then the accrued regret will be scaling as square root the number of items times the number of rounds. Now, clearly, there is an order-wise difference between these two regret guarantees, right? And this turns up in real-world experiments as well. We implemented our algorithm for two real-world datasets, Netflix and Movie Lens, and we compared the empirical performance, that is the empirical regret of our algorithm versus the UCB algorithm, which is a non-collaborative algorithm. Okay. So as you can clearly see, the regret of the UCB shown by the deep blue curve over here is way higher than the regret guarantees of our algorithm shown by the green curve. Okay. It turns out that our algorithm also outperforms a strong baseline, which is known as alternating minimization for this problem. Okay. Yes, please. Great question. So it's actually, there are two types of regret. One is called gap-free regret bounds, and the other is called gap-dependent regret bounds. So this is the gap-free regret bounds, which is also the worst-case regret bound. That scales as square root of t. If you go to gap-dependent regret bounds, then yes, it depends. The regret bound scales logarithmically with the number of rounds, but it depends on the gaps as well. Yes, lower bounds also match this one in the worst case. Okay. Because the regret does not depend on the gap, if you look at it. It's the worst. Oh, so what you do is you can convert the gap-dependent regret bounds to gap-free regret bounds as well by taking, let's say, a maximum over all the instances. So in the gap-dependent regret bounds, you also have dependence on the gaps, right? So you can set up the gaps to scale with the number of rounds, and you will get a gap-free regret bound. You can, yes, exactly. This is the worst case. Worst case over all possible gaps. Yes, please. I did, but for a different variant of this problem. I have not shown it over here, but there I was showing it. There again, empirically, we were seeing the similar kind of gaps. But for here, I did not show it. I just showed the main, the main point of this whole work is the difference between collaborative versus non-collaborative algorithms, at least empirically. Any other questions? Great question. I don't know of any such algorithm. Actually, I will tell you why it's very difficult to get one in the next few slides. And that's why we had to go through some algorithm built on a phased elimination framework. Okay. Okay, so in the remaining few minutes, let me take 10 minutes. Okay. So in the remaining few minutes, let me go into the algorithmic details of lattice. So what lattice does is to combine phased elimination with phased user clustering. Okay, so let us try to understand what happens in phase one itself. And if we understand that clearly, then it will be easy to follow the entire algorithm. I forgot to mention one thing. The lattice algorithm partitions the entire set of T rounds into phases of exponentially growing length. So there will be around log T phases. Okay, and the first phase has the smallest number of rounds. Okay, so let's try to understand what happens in the first phase carefully. At the very beginning, we place all the users in a single group. And the single group can be thought of as a very coarse cluster, right? It contains all the users. It doesn't know any information about the true cluster memberships. So all users are in the same cluster, okay? And we will make this group finer as we go along. And secondly, we do not know any knowledge of the true reward entries. So we keep all the items active or as candidate best terms for each user. Okay. Okay, great. So in phase one, we do something that is very similar to the exploitation component of the greedy algorithm. Again, for each user at each round, we randomly sample an item and recommend it to the user, get their feedback. Okay. But the main difference with the greedy algorithm is that in the greedy algorithm, we did random recommendations for a prolonged period throughout the entire exploitation component. But here, our goal is just to get a very coarse estimate of the reward matrix. We will be happy as long as the precision of the estimate is delta equals to half. Okay. So because our goal is to get a very coarse estimate in phase one, the number of sufficient rounds can also be shown to be very small. Okay. So what this implies again is that for a small number of rounds, briefly at the very beginning, we do random recommendations. We get the set of partial noisy observations. We complete the matrix using matrix completion again, low rank matrix completion. And once we use low rank matrix completion, we have an coarse estimate of the entire true reward matrix. And once we have an estimate, we basically have a coarse estimated embedding vector for each user corresponding to the estimated rewards, right? Now, what we can do is we can group users with similar estimated rewards. So for example, in this image, the top half of the users have been put into the same group because their embeddings, the reward embeddings, estimated reward embeddings were closer. And the bottom half, or corresponding to the blue region, has been put in a different group. So at the end of phase one, we have two groups of users. Okay, we have been able to partition the users into two groups in contrast with the single group that we had at the beginning of the algorithm. Great question. So we have a graph theoretic based approach to group the users. It also depends on this precision, delta equals to half. Okay. Yeah, I can go into more details about how exactly the similarity is computed, but let's do that offline. Okay. All I want to say is that the groups are made finer at the end of phase one, right? Now we also have to make the set of candidate items finer. So what we do now is we zoom into okay. Several clicks now. Or not. I'm not sure. Yeah, that's what is the estimated stuff. Okay, so what we do now is to go into each group of users. Okay, now for each user, we will say that its good items are those whose estimated rewards are less than 2 delta away from the empirical best item. This is the good set of items for the user. Okay. Now what we do is for each group of users, we take a union of this good set of items across the users in the same group, and we will discard all the items not in this joint set of good items. Okay. So for the top group, the one in brown, we will discard a large chunk of suboptimal items which did not belong to the joint good items. Those suboptimal items are not good for anybody in that group. Okay. Similarly, for the bottom half of users, we also discard a large chunk of items that are not good for anybody in that blue group. So basically, at the end of phase 1, we are left with 2 carefully constructed submatrices of the entire reward matrix. So at phase 2, what we will do is exactly what we have done in phase 1, but for each of these submatrices separately. Okay. So more generally, actually, before going to what happens in more generally, let me state some key intermediate results that we will show at the end of phase 1 itself. So for each user, their corresponding true best item always survives. Okay, this is easy to show because remember, for each user, we considered the true best items to be one that are 2 delta away from the empirical best item. So it's easy to show that with high probability, the best item is in that set. And since we are taking a union of good items across users in the same group, the best item for every user in the group survives. What is more difficult to show that each constructed group is a union of the true clusters. Okay, that is, our algorithm will not put some users from a true cluster into one group and the remaining users into another group. This will not happen. As a matter of fact, as I was saying, we have a graph theoretic approach for grouping the users, and we can show that users that belong to the same true cluster form a clique in that graph. So each group in our algorithm is a connected component in that graph. And therefore, we can show that each constructed group is a union of true clusters. Okay. The third difficult thing that we have to show is that for each user, the joint active items are still good. Remember, when we're taking a union of good items across the users, we are adding items to its good set, the good set of the user, right? So what we need to show is that good items for one user is also good for another user, as long as they both belong in the same group. Okay. And the final difficult thing to show is that each submatrix satisfies. Oh, there is a lag. I forgot. Okay. So each submatrix satisfies all the conditions that are necessary to apply the low rank offline matrix completion oracle. Okay. Yeah, so as I mentioned before, more generally, in the IIIT space, we might have several carefully constructed submatrices of the true reward matrix. And what we do is to do exactly what we did in phase 1 for each of these carefully constructed submatrices. The only difference is the quality of the estimates are increased exponentially with the phase index, which means that the length of the phases are growing longer. Okay. So now the question is, why phased elimination? As a matter of fact, this brings me to your question. Why not a variant of UCB or Thompson sampling? And the reason is, again, the offline low rank matrix completion. It turns out that it works only when the partial set of noisy observations are distributed uniformly across the entries. Okay. However, UCB or Thompson sampling gathers data non-uniformly. It puts, any online algorithm should put more weight on higher reward items as it goes along, right? And that's why our algorithm is based on a phased elimination-based framework, where we construct carefully the submatrices, but notice that in each phase, the data is collected uniformly at random from these submatrices, okay, which allows us to apply the low rank matrix completion oracles onto each of the submatrices. This is not possible if we had gone with a variant of UCB or Thompson sampling, at least to the best of my knowledge. Okay, so let me skip over the key steps in the proof. But the main thing is that we can show that the length of the phase, ith phase, is simply O tilde of items plus users by delta I square, where delta is the precision in the ith phase. And this follows from matrix completion guarantees. And if we add this number of samples across all the phases, we can bound the regret in each phase, and we can also bound the overall regret and get our desired guarantees. So let me also skip the simplified version of our algorithm in the interest of time and move on to our conclusion. Okay. So we have shown that modern recommender systems have millions of users and items, and non-collaborative algorithms suffer from a large cost. On the other hand, collaboration significantly improves the regret of bandit algorithms. Okay, so first we showed a greedy algorithm, which has suboptimal dependence on the number of rounds. And next, we showed our main involved algorithm called lattice, which is a phased elimination algorithm. It gets minimax optimal regret guarantees and combines phased elimination with phased user clustering. So basically, it does joint exploration, exploitation, and user clustering. Okay. And finally, I did not have time to talk about this, but we also have a variant of the greedy algorithm with soft commit instead of a hard commit. And this algorithm shows great empirical promise in the healthcare data that I talked about. Okay. And finally, let me just discuss a few other results that I have. As I mentioned, that we can also consider the more general setting where we only have the low rank structure instead of the cluster structure. This is a more general problem. And it turns out that we also have an optimal regret guarantees for the rank 1 setting. Okay, this was published in ICLR 2023. We also have near optimal regret guarantees for higher rank settings, but under another assumption that we call the hot items assumptions. This is far more relaxed than the cluster structure assumption, and is very popularly used for non-negative matrix factorization. Okay, this work has been submitted to NeurIPS. And we also have optimal regret guarantees with the blocking constraint that many of you asked. And this is also a NeurIPS submission. Yeah, so thanks everybody for your time, and please ask me any questions.
So if you have any questions, you can ask.
Maybe wouldn't it be possible to, just thinking of an alternate algorithm on how to approach it. So using the initial rounds, let's say in the initial round, I recommend the same item to all the users. Right? I randomly choose an item and recommend the same item to all the users. And from that, it's very easy to find the clusters, right? Because same item has been recommended to all the users. I mean, people in different clusters would react differently. So you will be able to figure out the clusters from that. And once you figure out the clusters, it's a very easy problem. No, it's just, it's just for each cluster, you just need to have the vector corresponding to preferences.
Right, great question, actually. So one big caveat of this is that this is actually a greedy algorithm, where you do the clustering first, and then you solve the remaining problem. What if for some clusters is actually not easy to separate the two clusters at the beginning? And then you will be spending a lot of time in clustering them because you will need a lot of samples.
Then those two clusters will be close together, no?
Yeah, but what if it's not so close that it can be considered as a single cluster for the entire duration of rounds? Think of a single user multi-arm bandit optimization problem again. We have several arms or items, right? And they have different gaps as compared to the best item. So what any algorithm does is to try to discard suboptimal arms gradually, right? Think of two arms which are very close. You might recommend, you might pull any of those two arms and still suffer a small regret.
No, I will randomly choose an item so that that kind of instances will not.
Right. But all I'm saying is that the clusters might not be easy to separate. Just like two suboptimal arms in the single user case might not be easy to separate. They're not necessary to, it's not important that we separate them until at a much later stage. We cannot go on not separating them, just like here as well, but we should not separate them right at the beginning. Let's say that. If we spend all our samples on clustering them, even when they can be considered to be a single cluster for quite some time, because you see my point, right? For the entire duration, when you are trying to cluster, you are not recommending good stuff. You are simply recommending random items again. right? So all I want to do is the algorithm that will give you optimal regret is to do joint exploitation and user clustering. Because if you go on recommending random items at the beginning to achieve some objective and then solve the remaining thing, it's a greedy algorithm again. It has the same problems as the greedy algorithm that I showed you.
There are millions of items in practice.
Right. So how can you also choose the best items? Items are even larger than the number of rounds. Think of it in the following way. The number of rounds is much smaller than the number of items that are available.
Have you looked at a best arm identification version of this?
Great question. We are looking at it.
And since he said that there are millions of items, you'll typically map an item maybe to some score.
Right.
This naturally brings you to Gaussian process bandits.
Right. Great
Are
question.
you looking at that as well?
No, not now. I should. Hmm. So the base term identification problem corresponds to the matching.
Best term is like you are assigning the highest probability to the
Right. Yeah, that is exactly what I was thinking.
Yeah, not matching, but yeah, I wanted to get this.
Right. I mean, probably we are going towards the same problem.
Yeah.
Right. I mean, at the end, if the best term identification problem, then our goal is to identify the best term for each user. Yeah, as he's mentioned that the matching constraint will not be satisfied, right? Because many users will have the same best item. Yes, please. Yes, definitely. This one? Oh, okay. Yes,
You have optimal regret for rank 1 setting.
right.
So is that is this talk that you gave a generalization of that? Because rank 1 is basically a special case of low rank.
Rank 1 is a special case of low rank.
And here you have optimal guarantees as well. So does this generalize truly the result of ICLR 2023?
No. The reason is that the cluster structure is also a special case of low rank. If you think about it. If the number of true clusters is C, the rank is at most C.
Yeah.
So the rank 1 setting is different, let's say, from the rank 1 assumption is different from the cluster structure assumption. The cluster structure assumption has can let's say encapsulate the setting, some settings where the rank is higher. But for
So let's say you normalize for the row. Yeah. So then the rank 1 setting is going to be 2 clusters. Either you multiply by 1 or minus.
That's a great question. I mean, great point. Like, yes, actually for the rank 1 setting, there are 2 latent clusters. One where the users have, the best item of the users have basically is positive, let's say embedding. It's a +1 or -1, exactly, basically what you, in short. But the rewards are not identical across the different users in the same cluster. This is something very different from what we have over here. Normalized by what quantity? But you don't know that, right? Yes, if you normalize it appropriately, you're good, but you don't know that. So in short, it's different, let's say.
So I guess there are no more questions. So let us thank the speaker again.
Thanks again for attending this talk at such a late time.